Right, our first example. We've got an ambulance moving at 35 meters per second. It's blowing its siren. It emits waves at a frequency of 400 Hertz. Calculate the frequency heard by a stationary boy when the ambulance is approaching him, moves away from him, and then what will the observed frequency be as the ambulance passes the boy? Sorry, I see that it's D, E, F instead of A, B, C. It's the numbering story of the computer. Kind of. Okay, so what do we have?
We have the
Velocity of the source and the velocity of the listener. That's naught. And we've got the frequency of the source, 400 Hertz. And we know that they move towards each other. So if the source so the listener is standing still and the source is moving towards him. So what will the situation be? The frequency of the listener will be bigger than the frequency of the source. So we know this is the thinking that we do before we start solving the question. To write down the complete equation, FL no, please write it down like this, otherwise it's mean people out there.
And then times by FS.
Okay. Now they didn't say anything in this question, but the average speed of sound in air is 340 meters per second. I expect that they will tell you what it is that they want you to use, because the speed of sound in air is not a constant. It depends on the temperature and the air pressure and all those things. So this is the speed of sound in air. The average speed of sound in air. Okay, so we've got 340 plus 0. Okay, can I leave that plus 0 out there? Okay. And at the bottom,
340 minus 35.
And then times 400. Okay. Cassiopeia it, please.
445, comma
9.
Yeah, 90.
Hertz.
Yeah.
Perfect. Right, are you ready for the next one? Okay, number B. They're moving away from each other. So the source is moving away from the listener. I'm trying to indicate that by the arrow between the S and the L. So what will the effect on the frequency observed be? It will be less than Fs. So we write the complete equation down and then we substitute. So FL equals V plus minus VL, which is naught, divided by V plus minus Vs times Fs. And now we do our substitution. So V is the velocity of the
340.
340, and the VL is naught, so I'm going to leave it there. And the 340, and what must happen here? Plus 35 times 400. Let's give
362.67
hertz. Yeah. So the same walk allocation will apply for that one. Number C, at that moment when the source passes the listener. Now above those little circular waves, the wavelength is 10 meters in the example that we did in the video. So it's only ahead and behind that the frequency, that the wavelengths change, so that the frequencies will change. Next to, no changing frequency. So the frequency observed by the listener at the moment the source is passing, at that split second moment,
400.
is 400 hertz. Do you understand that?
Yes.
Just when the one passes the other one. So when the source and the listener both are stationary, the listener will observe the frequency that is emitted by the source. And the second thing is when they move past each other, at that split second moment, the frequency that will be observed will be the same as the frequency that is emitted. 10 more minutes. When we drew those diagrams that showed how the waves ahead is stretched, is compressed, and the waves behind, the waves behind is stretched out. When we did that explanation there, the wavelength that is next to the source, that wavelength, didn't change. Now remember, I'm putting it on paper in 2 dimensions, but it's actually all around in 3 dimensions. So if the listener is standing on this side, the frequency that he will hear will be greater than the frequency sent out by the source. When he's standing behind the moving object, there the waves are stretched out, so the frequency observed by the listener is less than the frequency that is emitted by the source. But if you stand next to it, those frequencies, the frequency that the listener will hear is the same as the frequency that the source is sending out, because there the wavelength isn't changing. The wavelength is only compressed ahead of the moving object and stretched out behind the moving object. But next to it, it's not stretched out or compressed.
So now the question says what will the observed frequency be as the ambulance passes the boy?
Yes, so the boy is standing there listening to the waves that are coming towards him. And those waves will have the same wavelength as a stationary source.
Push off the line and you come through to the office, please.
So now when you're looking at when the ambulance and the boy are on the same line,
Yes.
not when the ambulance is past the boy.
No. At that moment,
So even if the question says that what is the frequency observed when the ambulance passes the boy, you look at the frequency that's observed.
as the ambulance passed the boy.
So as means
At that split second moment. The moment he's passed, he's moving away, so the frequency will drop again.
So if, like, let's say they want the ambulances, when they want the frequency of the ambulance past the boy, what like will they say? Will
Then
they
it's
not
D.
say as?
Yes, it will. They will say, he's moving away from him. He's approaching him. He's moving away from him, and then in the middle, between the two, is when he passes it.
So as
As he
that
passes
moment,
it.
when past it.
Yeah.
Now.
Okay. Can I move on?
Yeah.
Must I wait?
No.
Talita, are you alright? Right. Number 2. What do they say? A police car moves at 40, blowing its siren, so that's VS. 40. And emitting a sound at frequency 350. So FS is 350. Okay. The police car is chasing a robber in another car moving at 35 meters per second. So is this the listener perhaps? Okay, so VL is 35. He's going slower than the police car, so he'll hear an increased frequency. Am I right? Calculate the frequency of the sound waves observed by the robber. Okay. To sketch the situation, you've got the source and you've got the listener. What's the source doing?
The source is
Moving towards the listener. What's the listener doing? Moving away from the source. So you get the idea. Okay. So first of all, you write down the complete equation. Okay. Now this is a tricky one. I haven't really discussed this one. Yes.
Can you see this question later? Thank you.
So our speed will keep it at 340 unless they tell us it's something else. What's the listener trying to do? Running away. So what is he trying to do? He's trying to decrease the frequency observed. So what must I do here? Minus the 35. I hope it's making sense. Then we've got the source. What's the source doing? Chasing after it. What's he going to do?
Wants to make it
So he's also wanting to increase it. Am I right? So this must minus again.
okay.
Times 350, sorry. Because the listener is running away or driving away from the source, the effect of that part is to decrease the frequency. So the numerator must be a minus. But the source is chasing after him, and the effect of that will be to increase the frequency. So what must I do there? The denominator must get smaller. Yes? Okay, so what is the frequency that he will actually observe? 355, comma 83. Good.